Hello, everyone. I am Nora Hovey, Director of Chapters, and I am very pleased to introduce Aastha and Jen. They're going to share with you about a deployable AI Martian habitat. I think that's enough. They're with Mars Society Canada. I did want to get that in. Aastha, Jen, you have the floor.
Thank you, Nora, for the great introduction. So, hello, everyone. I hope that now we are moving closer towards inhabiting Mars from our wonderful morning presentations and technical lectures. Before I begin, guys, I want to ask one question. Why do you think that we should move to Mars? So, my personal motivation is, for me, it's also about reaching the Mars, but the more important thing is testing our human intelligence and our capabilities, that how far we can go with this. So I'm Aastha. I'm an architectural concept developer at Mars Society of Canada, and other than volunteering at Mars Society, I work as an architect in Vancouver at ABA Architects. And here's my co-author.
Hi, I'm Jin. I'm a Mars engineering developer at the Mars Society of Canada, and I'm a fourth-year undergraduate mechanical engineering student at the University of Waterloo in Canada. I'm really excited about the possibilities that exploring a brand new world has for our generation. And I'll be delivering the second half of this presentation about the engineering behind our Mars habitat. All right, next slide, please. All right, so speaking of engineering, Mars presents lots of really unique and difficult engineering challenges. And it's going to drive a revolution in architecture. Firstly, the atmosphere is inhospitable. The pressure is almost a vacuum, and it's almost entirely carbon dioxide, which is unbreathable. The fine dust might infiltrate into mechanical joints and seals and cause them to jam up. The temperatures are inhospitably low, -80 degrees Celsius. Because Mars doesn't have a protective magnetic field, you are at risk of particle radiation from solar storms and galactic cosmic rays. And finally, living in an isolated, confined, extreme environment, much like quarantine is right now, has a strong psychological impact. And we're hoping to solve all of these problems.
So, welcome to our artificial intelligent habitat called Project Thorpe. Thorpe is a Greek word for an habitat. These days, space architecture is becoming very important because it helps us to understand what are the various challenges that we need to face while designing on the other planets. Let's say, for example, atmosphere, gravitation, radiation, and everything that Jean quite described in the previous presentation. So these days, more and more space architecture is being into consideration. So there are two ways that we can carry a habitat from Earth to Mars. One, we are very aware, is inflatable structure. What are inflatable structure? They are basically, it is composed of inner and outer layer of fabric, and it has a typically very same material. The cavity between the walls is pressurized with air, making the structure rigid. The large structures can be deployed from small initial volumes and masses, and it makes them mass efficient. The interior of this kind of inflatable structure is also pressurized with breathable air, allowing astronauts to live inside without the spacesuits. So there are various advantages of using this kind of inflatable structure. One is the mass of the air and fabric is so small, so it allows the maximum volume to be deployed. It minimizes the amount of raw material being used. Also, the low mass makes inflatable buildings very portable, easy to transport. Also, the system is very complex because they are just air pressurized. The main focus of our today's presentation is about introducing you guys to deployable origami structures. So deployable origami structures, they are an origami, they are in Japanese art form of folding. For example, if you have noticed an umbrella, how the umbrella unfolds, or let's say the solar panel recently by NASA introduced into space. So the main benefit of origami is it can be easily deployed and collapse, and still the structure remains rigid under the loading. They deform along the crease lines. And these days, origami is getting much attention as it is easy to build 3D structures with it. And a lot of various shapes can also be testified. So origami structures, why do we choose origami over inflatable structure? It's because origami has more precisely predictable and reliable modes of deployment and collapse. It has a robust deployed structural strength and rigidity. It also reduces the supplementary gas and supplementary inflation gas for the air pressurization system. And also the ground testing and also it is very affordable to do the ground testing due to its less complex structure. And after additional rigidization can be attained after deployment, while further it improves the long-term structural strength. The key risk, there are a lot of risk in inflatable structures because they are unpredictable, they have lack of durability, it has difficult manufacturing, and also difficult maintenance and repair. Let's say, for example, we got a puncture and an inflatable structure, it becomes very difficult to repair the puncture and still keep the same kind of performance of the building or the habitat. Whereas in origami, we can easily replace it by the panel. So this origami has a lot of different kinds of patterns. While studying my research, I came across the most famous and most used patterns. One is the, I'm sorry, oops. So one is the round ridge pattern, the another one is the Taji pattern, the magic ball pattern, the Kuromira, bellow folding, as you can see on your right side of the table, Yoshimura, and the crystalline pattern. So I try to compare all of these different kind of patterns in terms of their deployability, rigidity, stability, pattern complexity, and the design application. As you can see on my screen, the bellow folding, the Yoshimura, and the crystalline pattern are one of the most competitive one when I compared because they have very good amount of deployability. They are very compressed. They can be very compressed. They are very rigid structure. They're also sealable, and the pattern is complex, but it is quite durable. The one thing with crystalline is it allows us to have enclosed space, and we can form a modular structure. So what are the different advantages of using origami, let's say? So it has an efficient packing, the shipping and handling is easy, the deployment, we can do it in a gravitational environment and also the polar environment. Also, it has an adaptability to uneven and rough surfaces. It is reusable, reconfigurable through joining of large components. Electronics can also be integrated. Let's say, for example, we can introduce some folding panels with solar panel or window systems. It has a structural health monitoring over long periods of time. It has an easy integration and long-term survivability, multi-use performance, damage tolerance, flat folding, and quick fabrication and assembly. Reduced material usage. Why reduced material usage is because we exactly know what are our geometric dimensions and considerations, and exactly those dimensions can be carried forwarded to an industry to manufacture it. And also it has improved strength to weight ratios. After considering various different kinds of patterns, I chose to go for a crystalline pattern, which is here. The reason I go for the crystalline pattern is because it has a very high compression ratio. A large surface can be folded very flat with minimal creases. This means we have fewer hinges and it improves the strength. It is very important to have less amount of hinges while doing a deployment on Mars. And also we have a diversity to explore other polyhedral shapes. So basically I will show you how we can get the very simple form of crystalline pattern is, let's say for example, we roll a paper. So if we roll a paper and then if we just like twist it, so it forms a buckling pattern, which is the crystalline pattern. I think my paper is not super nice, but I can try it. Yeah. So, okay, I need to have a very hard structure on the sides. I'm sorry, guys. but it's just like a very simple buckling, twisting, fold. So one of the next step, I wanted to move forward. Like we wanted to make sure that whatever we are understanding about geometry is also practically possible to do it. So we tried to integrate artificial intelligence. And there's a software called Rhino. So what do is we start sketching our origami pattern in a CAD program, and then we transfer this CAD drawings to Grasshopper software, where we give the algorithms, we give each and every command in the computer to fold and to unfold. The main advantage of using artificial intelligence is it allows us to make various considerations. Let's say, for example, I increase the radius, then it will immediately calculate the number of folds we require, the additional surface area, the additional surface volume, and everything, which is not quite possible to do by manually. And also artificial intelligence gives us very accurate results. So this is the Yoshimura pattern, which we did testify. Also, this result is achieved by using relative geometry transformations between the input parameters. And this pattern is also used to study cross-link pattern, which could be enhanced by exact node functions, which define the geometric transformations. This is a very totally new concept. These days, artificial intelligence softwares are still under considerations. So guys, don't freak out when you see this. Very complex mathematics. To be very honest, even myself, I'm trying to understand how exactly this geometry works, but I will try to make it as simple as possible for everyone to understand. So basically, the first thing we considered is we want to go with an hexagon structure. So we have six sides of the shape, and all sides of the shapes are equal with equal panels. So this is the folding pattern of the hexagonal structure, for which you can see the 3D picture on your on the top of the right corner. So first we fold the paper like this, and then we make the valley folds. So the cross-link pattern is actually a very self-structuring process of thin wall of cylinders under torsion load. And this pattern can be generated without the manual creasing process of valley and the hill folds. Like I said, you just make a cylinder, make a solid cylinder, and then just twist it. It's gonna create a cross-link pattern. And also this folding and the unfolding produce a very pop-up effect in single or multiple twisting units. This pattern is also very favorable for modular configurations, as this allows us to enclose the structure. So when all the triangles in the structure which make up the pattern are all identical, this is a phenomena which is also called cyclic symmetry. Concluding that this kind of phenomena provides great design tools and applications, not only formally but also structurally, opening new perspective of design strategies and research topics. So let me introduce you to our very basic drawings of our habitat. So this is the east elevation, west, plan view, north elevation, and the south elevation. And this is the perimeter of our structure. This is our exact folding pattern. So first we fold it to the dark black lines, and then we angle them at 37 degrees with these green creases. So the most amazing thing about this structure is when it is folded, when it's compressed, it has 125 cubic feet. But when it is deployed, it has 1524 cubic feet, which is almost 10 to 12% more area. And it gives a surface area of 650 square feet if we take these dimensions. Basically, we try to go with a very simple steps. So we did design only for the crew capacity of 2, and we have an atmospheric pressure of 1 atm. For now, our power source is solar panels, but also one fact to consider is Mars only has 40% of the solar energy, so we might consider nuclear energy in future. So how does our deployment works? I created a very short video to understand how this deployment works. Also, don't freak out when you see the very big, complicated maths on your left side of the screen. So as you can see in the video, how our pattern is folding and unfolding. I try to create a sequence of folding and unfolding, and you can see that on your right side of the corner. So the first picture, the most compressed state is the panels are being folded at 35 degrees. The next one, let's say, is at between 45 to 50. The third one is 65, and this one is at 90-degree angle. So this is how our structure is folding and unfolding. So I will now like to forward the presentation to, sorry, what's that? To Jen. Yeah, to Jen.
All right, thank you, Aastha. And just, okay, here we go. All right, so when we're supporting the habitat on Mars, it's going to be put on uneven ground, most likely. And we'll need a way to secure it to the ground to prevent it from toppling over. So there are a few ways we studied you could do this. You could screw it into the rocks using a ground screw, as you see on the left. You could use spinnakers to support it, or you could even suspend it on a truss structure. And the advantage of suspending the structure above the ground is that it minimizes ground contact, which means that when the ground gets really cold at night, it minimizes heat losses by thermal conduction. You can see in the video at the bottom, you can deploy and collapse the habitat by simply making a twisting motion. But when you apply a compressive load to it, it actually becomes quite stiff, as you can see there. All right, next slide, please. And one of the advantages of using an origami habitat over an inflatable concept is that because the rigid panels don't need to be flexible, we have a much wider variety of materials we can use, and we can use them much more creative ways. So our panels, they need to be lightweight because they need to be transported to Mars and around Mars. They've got to be strong to resist both external loading. For example, if you pile a regolith on top of the habitat to block out galactic cosmic rays, or internal pressure from the air pressure. It needs to be effective shields against particle and ultraviolet radiation from the sun and from the cosmos. It needs to be good thermal insulators because Mars is cold, as we all know. Corrosive substances in the regolith, like superoxide, can actually eat away in materials such as plastics, so it needs to be resistant to that too. And in order to make this feasible to manufacture in the long term, we wanted it to be made of materials that are feasible to manufacture with Martian materials and industry as well. The solution we came up with is to use a sandwich of various different materials to fulfill all these requirements. These panels also need to be able to move and swivel, and for that you need a mechanical frame with hinges. These need to be able to exclude dust and fines to prevent them from jamming up. They need to operate in a near vacuum environment because of Mars' thin atmosphere. And because Mars gets so cold, we need to ensure that they don't seize up at low temperatures and that they are not vulnerable to thermal expansion. Next slide, please. So here's an early conceptual panel design just to give you an idea of how we could leverage the properties of different materials. You could use aluminized mylar, which is extremely reflective, to minimize thermal radiation losses on the outside. Layers of high-density polyethylene, or HDPE, could be used as a shielding for proton radiation from the sun, which comprises the majority of radiation on Mars. Kevlar and Vectran, which have extensive space operations heritage in spacesuits and in Bigelow's inflatables, I think that was mentioned in the chat too, will be used to provide tensile strength to hold in the atmosphere and to provide flexible sealing. And aluminum 2219 has been extensively used in all kinds of spacecraft from the SLS to the Falcon 9. And this will be used to provide strength and rigidity to resist the bending stresses from atmospheric pressure to inside and to simply provide more compressive strength. Next slide, please. So in order to keep warm on Mars, I did a thermal analysis. There are three ways you can lose heat: convection from the atmosphere carrying away heat, thermal radiation, and by conduction to the ground. We can mitigate conduction to the ground by suspending the habitat above the ground. And as for convection, convection is actually quite a manageable loss because the Martian atmosphere is so thin, it's actually quite inefficient at carrying away heat. Its pressure is only 1% that of Earth at sea level, even though it's at negative 55 degrees Celsius. So it's actually not too difficult to maintain an internal temperature of a comfortable 20 degrees Celsius. The radiation losses are mitigated by covering the habitat in aluminized mylar, which has only a 2% emissivity in the spectrum of interest. Just to give you an idea of the kind of problem we're dealing with, if you had just 1 centimeter of high-density polyethylene as insulation, A 3-meter long section of this habitat will require about 1.3 kilowatts of heating. And to give you an idea of how much that is, that's about the amount consumed by a household microwave. And this can be reduced substantially if we use vacuum insulation panels to take advantage of the low atmospheric pressure. Next slide, please. As for the mechanical frame, this is the part that allows the panels to rotate and swivel. If we leverage composites such as carbon fiber, you can get really high strength to mass ratios. On Mars, you could use composites such as basalt fiber, which can be produced on site and has similar properties. Using conventional ball bearings made out of steel and using oil as a lubricant wouldn't work because at the very low Martian pressures and temperatures, the lubricants would either freeze or boil away. Fortunately, there's a solution. If we use Teflon bearings, they don't need any lubrication at all. The Teflon slides against each other with a very low friction. To prevent this has been used on Mars rovers as bearings because for these conditions specifically. To protect the mechanical parts from damage, we have 2 layers. On the inside, we have a pressure bladder which holds in the atmosphere. That will be made out of Kevlar or Vectran. And on the outside, you have a thermal and dust cover which will be reflective and will keep the dust out. In this way, the mechanical parts are completely isolated for the entire operational life. So overall, what we should take away from this is that while the idea of an origami habitat is quite novel, the engineering behind it has actually got a lot of space operations heritage, and it's actually not that new. All right, let's move on. So this is a schematic view of the mechanical parts. So the red lines you see there are rigid hexagonal shapes. These give the habitat its hexagonal shape. The black lines are pipes that are used as hinges. And these are the lines about which the rigid panels will rotate. And finally, the green dots at the vertices, those are ball joints, which will allow the rods to swivel. And by having these components arranged like this, the habitat can be used with the Kressling origami fold. And it can twist to contract and twist to expand. And as you can see on the right, using composite materials such as carbon fiber can give us a great weight advantage. Next slide, please. All right, so here's a little concept of how a Mars base using these habitats might look like. If you look at our Zoom backgrounds, you can see that we've also got some more concept art there. Let's talk about what kinds of activities you could do with this. Next slide. Okay, so here's a bit of this is kind of what inspired the project. We haven't seen any other project besides ours and this in origami habitats. So this is an origami habitat concept by Yakovlev Daniil. I hope I'm pronouncing his name right. So essentially what he's doing, he's using the Yoshimura fold to create a permanent Mars habitat. Right now, our habitat is designed just for temporary usage as a temporary shelter. But hopefully in the future, what we plan to do is to expand the concept because it's scalable to add in things like labs, hospitals, dedicated sleeping areas, and cooking facilities. Let's move on.
Welcome to Mars. Sorry.
All right, now let's move on to the practical testing. So one advantage of this project is that we don't need Kevlar to test this or to sew flexible materials together. We can make it out of rigid materials such as cardboard or coroplast, corrugated plastic essentially. What I'd like to do is I'd like to be able to test this Kressling geometry and find areas for improvement in a real operational setting by evaluating it at the Mars Desert Research Station. The test case we've come up with is to evaluate its utility for a 2-person EVA team. They would use the origami habitat as a temporary shelter for an overnight rover sortie. And we will need to test whether the habitat has enough space and the correct geometry to perform all the necessary activities on the inside. Next slide, please. So I plan to test this when my rotation at the Mars Desert Research Station in May next year. I think there's a couple of my crew members in the audience right now. And I plan to construct a mock-up from cardboard and corrugated plastic. The idea is that to run the experiment, 2 of the crew members would take this habitat out to the site, and they would simulate all the different activities that a real expedition crew would go through, such as transporting it to the site, deploying it, repairing your EVA suit, examining your science samples, and then in the morning, packing it up and taking it back. And by going through all these simulations in a Mars analog environment, you would get as close as you can realistically get to actually testing it on Mars. If you'd like more information about our mission, you can go to mdrs228.com. All right, and
we welcome questions now, I think.
And so that's the end of our presentation. We'll now take questions. Just go to the last slide.
I am going to combine similar questions here. First off, this approach, is it suited to using once we get established on Mars, or is this more at the front end of the Mars mission and to get us to Mars?
I think you have great applicability at all phases of Mars exploration from the very beginning, because you could use it either as a temporary shelter for scientific expeditions, or you could expand it to be used as a permanent settlement as well to enable easy construction. Aastha, I think you wanted to add something on?
Yes, I think, so we don't know yet. Of course, we are definitely trying to establish different kind of 3D technology for our Artemis mission and for our Mars mission as well. But I think this is something very technical and which can be tested on the Earth. And I think it gives a very specific results how the system works. So I think it is very possible to carry one compressed structure, origami structure from Earth to Mars, because when you fold the structure, it can be carried in a shipping container. For whatever size of habitat, it is just the container sizing will be like 2 meter by 2 meter by 2 meter, which is quite affordable to carry. So I think it has a various purpose. And in future, as Gina mentioned in the presentation, that we are also planning to consider a lot of different kind of activities that we need to perform on Mars. For example, let's say EVA, the chemical labs, the bio labs, the emergency labs, the medical center, and everything. So in our further research, we're gonna make it as sustainable as possible with this kind of origami technology. I hope that answers the question.
Another question, have you considered how these structures and radiation would, in other words, how do you plan into these structures, the radiation consideration?
Yeah, I think I mentioned that earlier in the material selection. So the most basic layer of protection would be integrating high density polyethylene into the walls of the habitat. And the reason we use high density polyethylene is because it's rich in hydrogen. And hydrogen is very good at stopping particle radiation from the sun, which is mainly proton radiation. And that's what constitutes the dominant source of radiation on Mars. You could, if you wanted to, you could get even more radiation shielding by just grabbing a shovel and shoveling regolith over, covering the habitat in regolith, so that you are more effectively block out proton radiation, but you also block out cosmic rays as well. So that's how we could do it.
Can you discuss the costs that would be associated with this approach? Is it cheaper, more expensive? Is it not able to be determined at this point?
So I think we did have our basic consideration of cost. I cannot right now say in $1 million or how much it's going to cost us, but we do have a lot of projects being already done on Earth. And I will show just example here. Let's say, for example, okay, it's inflatable structures. So I think it is this technology is more cost effective as compared to inflatable structure, because inflatable, we don't have quite calculated material usage, or it is not quite possible to repair if we are building up. Also, those kind of materials are very expensive. So I think this is a very cost effective, as we can first try to make it with the cardboard, and then we can try to go further and make it with an aluminum panels, and then we can go and then use exactly kind of materials like HDPE and everything that Jean has explained. But I think this will, whenever we come to that stage to exactly know how much it's going to cost, I'm pretty sure that it's going to be more cost effective, or maybe one of the most cost effective solution right now, which will give some technical safety calculated risk.
All right. Last question. Can you discuss this structure's ability to be pressurized?
I think the main consideration with this kind of structure over an inflatable structure is that because we have flat surfaces, they're prone to bending stresses. So essentially, if you pressurize the panels like this, they'll tend to bulge outwards. But I think that that's not an intractable engineering problem. You could increase the stiffness of the panels by using vacuum insulation. So that would increase essentially increasing the thickness of the panels and leaving a vacuum in between. That would increase the stiffness of the panel without increasing weight too much. Alternatively, an even stranger concept I thought of is that you could even simply have a frame and fill the gap in the panel with a flexible material so that it is allowed to bulge out a little bit, which would relieve some of the stress.
All right. Excellent presentation, Jin and Aastha. We are out of time. If someone wants to contact you with further questions, where would they go?
So to contact me, one can write an email to aastha.aastha. So it's Aastha, AASTHA.KACHA, as you can see on the screen, @marssociety.com.
.ca.
.ca.
Yeah, and if you want to find us, go to marssociety.ca. That's the website for the Mars Society of Canada. You'll find lots of cool projects that we're doing and keep up to date with everything we're doing. And our contact information is there. You scroll down a little bit and go to this team section. You can click on our profile pictures and you'll be able to contact us.
All right. Well, thanks again. Thank you, everyone, for attending.
Thank you, Nora, and everybody who came.
Yes. Have a good evening, everyone.
Thank you, everyone.
On to Mars.
Yes.
On to Mars.